we're going to just chat about the technical side a little bit. At ATEC, we really believe in open sourcing as much of the technology as we can, because we believe both in transparency, not only in terms of donations, but also in terms of software, and in terms of trying to help the community and support the emerging blockchain community that is growing every day. This is my work and the work of Nicola. So I'll hope you'll enjoy it. Just a little bit about ourselves. I'm the CTO and the Chief Data Scientist at ATEC, and I have been working a lot on developing blockchain solutions that can be easily deployed, because one of the challenges of deploying networks like Hyperledger Fabric is that you need to run a lot of commands, and you'll see all about that quite soon. I used to be a cognitive neuroscientist, and now I'm a technologist. Nicola, I'll tell you a little bit about Nicola. Nicola, he's an awesome blockchain engineer. He's responsible for our backend blockchain chain code, the smart contracts, and he is a perfectionist in the best of ways. He's contributed also to the Hyperledger Composer code base, and he's an awesome person all around. So we're going to talk about deploying different types of networks. At the very, very basic level, you might develop a network that is purely for development, where you just have in Hyperledger Fabric an order and a peer. And we'll get into those concepts of orders and peers a bit later on. If you don't know what they are, don't worry, we'll talk about them. If you're deploying an actual production network, you'll need something more. You'll need a certificate authority for all the identity stuff, the orders as a network doing the consensus, and the peers, multiple peers, for ensuring that the blockchain is alive, because you cannot just have a blockchain with a single peer. That's kind of weird, and only doable in a development environment. Really. So here's the code that we developed. We've open sourced it at github.com/atechnology/Nephos. Nephos being the Greek word for cloud. We have documentation. We've tried to make it quite detailed. If you don't, by the way, all this stuff can share with you the slides, so you don't need to take photos if you don't want to, if you're lazy. We'll send them to you, just ask us. And this presentation will have 4 steps. We'll talk about Hyperledger Fabric. A lot of you will know about it because you're at the Fabric meetup. And we'll talk about Kubernetes, and which is where we deploy our networks. And we'll talk about how deploying Hyperledger Fabric to Kubernetes works. And we'll show you why it's actually difficult. And finally, we'll show you a demo of how Nephos work and how it makes that hopefully easy. Okay. Hyperledger Fabric. So a little show of hands. Who has some knowledge of Hyperledger Fabric? Has used it a little bit? Okay, 1 person, 2 people, 3 people, 4-ish, 5, 6, 7. Okay, cool. Who knows what Hyperledger Fabric is, even if you haven't used it? Okay. Okay, so that's good. Then it's actually useful that I include these slides. So Fabric is a framework under the Hyperledger project. There's actually a multitude of different frameworks, including Sawtooth, Iroha, Indy, and so forth. Fabric is probably the most popular one. They have quite an extensive documentation. And Hyperledger Fabric is built with 3 types of nodes. Whereas in something like Bitcoin or Ethereum, you typically have one single type of node that does the consensus and everything. In Fabric, you have 3. One is the certificate authority. The other is the ordering service or the orderer. And the last one is the peer. The certificate authority deals with all the identities on the network. It deals with identities of the different nodes, of the orders and the peers, but also of all the agents interacting with the blockchain. It registers these identities and issues certificates, basically. The ordering service is based on orders, and typically in production you will have a set of them exchanging messages via Kafka cluster. In development, you can actually just have a single order, just checking that the blocks are correct and not doing much else. And the peers are the actual nodes that store the blockchain and that receive transaction proposals and check that these transactions are correct and then commit them to the ledger. We can actually attach a database, next to a database to these peers using CouchDB to actually maintain the world state so that we are able to query the blockchain state much faster than so that we don't have to traverse all the blocks and gather this information in a laborious way. Cool, Kubernetes. Who has heard of Kubernetes? Okay, and who has used Kubernetes? Okay, cool. So another set of slides that is not amiss. Kubernetes is a system for orchestrating the deployment and management of containers. You guys are familiar a little bit with Docker, yes? Yeah, great. Docker has had a lot of promise because it allowed the abstraction of the application in so-called containers. Linux containers basically enable you to run an application without caring too much about what is outside those containers. You can package all the dependencies of all the secret information that you might need into the container, and then you can run it, and you don't have to care whether you run it on Windows or Linux, on which Linux distribution. It allows you to basically isolate things. But managing Docker containers on raw Docker is a nightmare. So that's where Kubernetes appeared as a kind of development from Google's Borg system. And it allows you to make that much easier. To work with Kubernetes, we need to understand three core concepts. The first one is that there is a Kubernetes cluster composed of a number of servers. This might be physical servers living in your basement. They might be cloud servers, some virtual machines, basically. We also will talk about a little bit about charts, which are packages that pack together a set of Kubernetes resources and allow you to easily deploy an application made of different subcomponents. And Helm and its server-side tiller component allows you to install these packages or charts. The Kubernetes cluster basically allows us to deploy and scale and, importantly, self-heal all these containers. So if one of your container dies in a normal Docker environment, it will just die. Your application is just stopped. But in Kubernetes, when your container dies, the system, Kubernetes system will kind of check, oh, that container should be alive. We should resurrect it and start it again so that you can have much more robustness of your running applications. And it also takes care of all the connectivity inside the Docker cluster and with the outside world. So it looks a little bit like this. The Kubernetes cluster, you can think of it as a kind of black box. But inside the black box, you have a number of servers or nodes. Let's say we have 3 servers. And in one of the servers, you might have a set of Docker containers. These containers are actually grouped and contained by pods. A pod can contain 1 or more containers and basically manages their state and survivability, essentially. You can actually have deployments which can actually manage these pods. They ensure that these pods are continuously alive and resurrect them as needed. If you need to do an upgrade and you need to update the pods, the deployment will actually stretch across the different servers and kill only one set of containers before create the new version of the containers that you need, and then only pass to the next node and again upgrade there. And then you have things like secrets and config maps. Secrets and config maps manage your environmental variables and allow you to attach these to the containers that you're using. So that, for example, you might keep some passwords in your secret that the container needs to access some resource, or they might have some general configuration. They might have some label saying, "Oh, this is a development environment," or "This is contains some configuration file that we need to reuse." And we also have services which allow us to talk to a multitude of containers. So these can load balance between different. You might, for example, want to hit the service, and that acts as a load balancer to send your messages to a set of pods. And finally, we have the ingress, which allows you to actually access those services from outside the cluster via, for example, an IP address or a domain name. So, any questions so far? I covered a lot of ground in like a few minutes. All clear? Okay. You can ask me questions later also if you're shy. I'm shy as well, so that's all fine. Okay. Typically, this is what it will look to have a deployment of a peer or an orderer on Kubernetes. We'll have, for example, one of the deployments for the peer one on our first server, and we might have the deployment also on the same server of the orderer two. Inside, you'll see that there's a container, HLF peer, and a container HLF ord, and both of these might be communicating with the outside world via an ingress. And on the other nodes, you might have like order one and peer two, and so on and so forth. Question? You don't have to, but you can. Part of the reason of putting them on the same resources is on the same VM is just to show that you don't have to keep those things necessarily separate. You can reuse the same servers to maintain several of these different resources. You might have, for example, some other part of the application. If your server dies, these guys will get resurrected on a different server. And ideally, you'll have more nodes than this. You'll have, for example, another node, a few more nodes, so that if something of your some part of your network dies, there'll be some failover to actually for these guys to migrate to. Good question. Yeah, so there's also charts, and charts, as I described, they're kind of packages of different components. So you might group the config map, the secret, the pods, deployments, all together into a package that is templatable, so that you can use it as a cookie cutter and make a lot of Hyperledger cookies. And Helm is the actual installation system that actually does that. It allows you to package these charts and also deploy them. And then, for example, in our case, we will have one chart for the peer with all those components and one chart for the order with all those components. And we can easily cookie cut it onto our Kubernetes servers. So this is where we're going to look at the synergy between Hyperledger Fabric and Kubernetes and how we're going to be deploying this. I'm going to show you a really basic example. This is not what you would use in production. At the beginning, I was showing you something that was looking a bit more like production. In production, we would have multiple certificate authorities because we'd have multiple organizations, right? So each organization would have its own certificate authority to actually enroll their nodes and their agents. We'd also have multiple orders communicating with Kafka, so that we would have resilience, so that if that order, one of the order dies, your network still stays alive. Finally, we also would have more than one peer because that's the whole point of a blockchain network. It's a network, it's not a single computer. But this micro production setup is quite good for QA. You can run, if you want to kind of test something for your, in a kind of QA kind of integration testing environment, this should be enough. The first thing that we need to actually do is we need to install Helm on our cluster, which is basically, you can find that's pretty easy to do. And you'll also need to install an ingress controller and a certificate manager, because we need some of the components of the system to talk to the rest of the internet, especially the certificate authority, but also potentially the peers and the orders, depending on how distributed your cluster is. And we'll need to install the CA client. And you can do that with our Brute app, or you can use the script provided by Hyperledger Fabric. So the Fabric Certificate Authority only requires 6 easy and very lengthy steps. The first thing you need to do is to actually create the namespace for the Certificate Authority. We'll call it CAs in this case. Install the database to hold the identities. Install the actual Helm chart for the certificate authority that we created these Helm charts. Get the certificate authority pod and check that it's listening. This is the actual database values file, so that we can actually show that we have 1 GB for holding the identities and some anti-affinity. So this anti-affinity kind of relates to your question, because you can make sure that all these databases end up on different machines on Kubernetes cluster, and then they don't end up bunched up on single machine. Your single machine kind of dies, and then all your certificate authorities die. Similarly, we have a values file for the certificate authority. We can provide some host. In this case, we provide our own host, ca.nephos.8 tech-test xyz. It's one of our test domains. Please don't do any DNS attack on us, but it's okay. No, you can do. Fair enough. Some persistence and some name for the certificate authority, and we specify that the external database is the CAPG PostgreSQL. That's basically the service that we will be calling inside the Kubernetes cluster to access the database pod. We have some configuration stuff, and again, we have some affinity. We need to make sure that we end up on the same machine as the database, but on different machine to all the other certificate authorities. Then we need to create an identity for a certificate authority by enrolling our certificate authority with itself. And we check that we can actually access the certificate authority with curl. We then have, in this network, we have two organizations. We have an order organization, we have a peer organization. This is like one of the simplest setups you can have, because it's a micro production one. And this will be the administrators who will have the possibility of creating other identities. We enroll these identities after registering them. And we do a bit of shuffling of certificates around, because we need to copy their certificates to the admin certificate folder. We save the crypto material to Kubernetes with these easy to remember commands. And for the PR. And we use this config.txt file to actually define the network, right? So this defines an order organization. So that's where the administrator for that is working, and the peer organization. We define whether the order type is solo. In this case, it's solo, but we can actually find it to be Kafka. And the profile for this. So we have a Genesis block and a channel block. Then we can create the actual Genesis block using config.txtgen and save those secrets to the Kubernetes cluster. Now, the order is a little bit easier. In this case, because we're not using Kafka, all we need to do is to set up the order identity. We have a single order, so we actually register them with the certificate authority that we have, and we enroll them, which generates the crypto material. We save that crypto material in the same way to Kubernetes, and we install the Fabric order chart and check that it's alive, basically, by checking the logs. This is what it kind of looks like. It holds some of the secrets that we defined above. So it holds a certificate for that order, the key for that order, and also the certificate authority for the order admin and the Genesis and administrator certificate. Oops. And then we can actually deploy the peer. This will again be a little bit more involved. We need to install first the CouchDB and check that it's alive, again, with Helm install. So this is the simplest values file, because you just need to specify persistence and the type and the tag, as well as the anti-affinity to ensure that CouchDBs end up on different servers. Set up the peer identity. So we create an identity for the peer node. And again, we save it to Kubernetes. And we install the peer Helm chart, and again, check that it's running. Finally, almost finally, this is what the values file looks. Again, it has the identity information for that peer and also for the administrator, because you'll need some of the key for the administrator to actually create the channel. And once you do that, you can actually create the channel, which we mount the channel transaction onto the peer, and we run this simple command to create the channel. And we fetch the channel block, and then we join it. And then we can check that the actual channel is actually present on the peer. So who is confused by now? Raise your hands. Okay, so will you agree that there's quite a lot of steps, right? How long do you think this would take you to do, like if you had to do it manually? Oh, like, okay, let's find out how quickly we can do it with Nephos. Okay, so of course this bit will take a little bit of time. You'll need to clone our repository, cd to Nephos, and for best practice, we'll create a virtual environment with Python 3. Use Python 3, don't use Python 2. You'll source your virtual environment, which will allow you to use that specific Python version, and you'll install the requirements, of which there are not many. That should take a couple of minutes. So it will look something like that: git clone, cd Nephos, Python 3, blah, blah, source, activate, pip install. And you're basically ready to go. We have one configuration file, which we use to define the network, to define which cluster we deploy to, which chart repository we use for the charts. The charts that we created are on the stable Helm charts official repository, so they should be easy to find. We specify the configuration directory, where we store the cryptographic material, and the directory values. And we specify the CAs, so we have a single CA. We have two MSPs, so we have two membership service providers, the order administration, so organization, and the peer organization. And we have one order, in this case, one peer. And we can actually use Composer if we want, but we want to go into that this time. And then this is the command that you use to deploy that network. You might export to the environment, for example, QA, and you just run Nephos deploy -f, the file for the settings, and the fabric command. And that will deploy the entire network, running all those long and not that easy to remember commands. So demo, let's do it. Okay, I'm going to, because we're doing this on Minikube for demonstration purposes, I'll just need to create the certificate for TLS for the certificate authority so that we can access it by TLS. But this is basically in a real environment, you would not do it. You would actually have Let's Encrypt and the cert manager on Kubernetes do that work for you. And now let's actually check how long that it takes us to create this very simple fabric network. That would take us at least half an hour, maybe an hour to do it by hand. So first we install the database for the CA and check that everything is running. Okay, this is the time when the blue screen of death should appear. Microsoft Windows XP, anyone? Okay. Okay, this one takes a little bit longer because it needs to actually create a volume, so it might take a little while. Come on, don't disappoint me. You're a good boy. Yes. Of course, the live demo breaks after working 3 times in a row completely well. Oh boy. We're going to do a little bit of back fixing. Okay, I forgot to actually destroy all that stuff. Okay, never mind. Let's try again. There we go. Now it didn't exist, so now it's creating it. So, and we're going to time it. It should happen a bit considerably faster now. Status. Yeah, there we go. It's running. There we go. Okay. Now we install the certificate authority. That's this command. And we just wait for it to start. And once it started, we can get all the certificates. We create them. We create the Genesis block, the channel transaction, and we start the first order. And we install the CouchDB. And the peer. There's the peer getting created. And it's running, and we create the channel, we join the channel, and then we're done in 1 minute, 37 seconds. Yay! Okay, well done, Nephos. Oh yes, the thing that I wanted to show you, the next thing, is that we have put a lot of work into making Nephos solid. So we've have quite a lot of unit testing and integration testing on it. So the unit testing gives us 100% coverage for those of you who care. Basically, it means that it actually, the code works, and we're quite confident it works. And yeah, and we have further resources that you can look at. We actually created a chapter at the edX course, the official Linux Foundation course on Hyperledger Composer. We've also done a course on Pact, Udemy, and O'Reilly on Hyperledger Fabric and Composer as well, called Hyperledger for Blockchain Applications. We have also videos that are free. Actually, the edX course is free. The Pact course isn't, but it's like, I don't know, it's like 12 quid, I think. The videos are free. There's a webinar, and there's the official Linux Foundation webinar on deploying Hyperledger Fabric on Kubernetes, and that goes into more detail on all the commands. And there's the workshop, which we did at Hyperledger Global Forum, which is about 3 hours. You can enjoy watching the videos if you have that much patience, but it will give you a bit more detail into every single step. And we created the actual charts for that we showed you, and we maintain them. And we actually created also a chart for Hyperledger Composer, and are working on one for Hyperledger Explorer. Although, yeah, and we're hiring people for the front end, the back end, the blockchain, DevOps. We're looking for talent. Yeah, come join us.